Hello everyone, my name is Barış. Today I want to talk about the three-phase induction motors. So firstly I want to show the equivalent circuit of three-phase induction motor. If I explain it, you can see the stator resistance firstly, and after this stator inductance. And the right side is rotor resistance and rotor inductance. And the downside we have R2, it's core loss component, and we have XM, it's magnetization reactance, and the right side we can see the resistance showing strength. So we have model of the three-phase induction motor. We can see the inside it, and three-phase induction motors structure and features. Three-phase induction motors consist of two basic components: a stator and rotor. This one's stator and this one's the rotor. So the stator forms the fixed part of the motor, and inside of this part are windings made of animal insulated copper and insulated copper wire. The stators of three-phase asynchronous motors have a separate winding for each three-phase. The function of the windings creates a magnetic field when AC energy is applied, allowing the rotor to rotate. The rotor is the rotating part of the engine. It's formed by packing thin steel sheets on top of each other. So, in order of the rotor to create a second magnetic field with the effect of the stator magnetic field, cavities are opened on its body. Aluminum rods or coils were placed in the opened cavities. And ring induction motors have windings on their rotors. The rotor of squirrel cage asynchronous motors has short circuit bus bars. I will show it after these pictures, but I want to explain it one by one when I'm showing that. So, squirrel cage asynchronous motors are used in industrial applications. Among the electric motor types, they are the most used asynchronous motors. The usage rate of this engine is around 90%. Generally, three-phase asynchronous motors are used in workbenches. These engines are simple in construction, easy to operate and repair, and every electric motor has auxiliary parts such as bearing, cover, shaft, carrying hook, and connection terminal. So here we can see the stator and the iron core, the outside, and this one is stator slots, and stator winding is coming down. It's a lot of winding like this, here, all these sides. So, and we have two type of rotor. This one's the squirrel cage rotor. Generally we use this one because I think better than the wound rotor, and this one's the wound rotor. When we look at the wound rotor, we can see the laminated core here and coils little bit downside. But when we see the squirrel cage rotor, we can see the copper bars, lamination core, and metal rings. So now I want to talk about the working principle. When a three-phase alternating voltage is applied to the stator windings of these motors, a rotating magnetic field is created. This field causes a short circuit bar standing in the magnetic field and induces a voltage on the rotor. Yes. The short circuit currents created by this inductance voltage create the rotor magnetic field on the rotor. As a result of the interaction of the rotor magnetic field and the stator magnetic field, a torque is generated. With this moment, the rotor starts to rotate. This rotate starts to rotate in the direction of the rotating field. If the motor rotor rotates with cyclonic speed, the star field will be in line with the rotor short circuit bars. In this case, the rotors are not cut by the field, and no tension is induced in the rotor rods. Therefore, the rotor does not rotate as no torque will be generated. So after that, end bell and wheeling back again, lifting eye for the takeout because it's so heavy. Coast orange frame, the outside and stator coils, square cage rotor, this one's the rail, the square cage rotor, and bearing seals, ball bearing. So, and now, what is slip in an induction motor? In an induction motor, slip is a speed between the rotor as well as the rotating magnetic flux expressed for each unit of synchronous speed. It can be measured without dimension, and the value of this motor cannot be zero. Yes, in this motor, if the power supply 3-phase stator winding is 3-phase, then a rotating magnetic field can be produced inside the air gap. So this is known as synchronous speed. The interface between the rotor current and the rotating magnetic flux can generate a torque. This, according to Lenz's law, the rotor starts to rotate in the direction of the rotating magnetic field. As a result, the relative speed is regulated to cause slip inside the motor. And now I want to talk about the torque production of 3-phase induction motor. AC motors works on the principle of a rotating magnetic field, that is, the armature windings in the stator energies equality. A phase, then B phase, and then C phase, and so on around the stator, creating a magnetic field that surges on each phase winding. The strongest part of the field moving in circular path around the stator, a single-phase AC induction motor needs to have start winding and a phase splitting and shifting device. So this one's typically switched capacitor. So built into stator to have a rotating magnetic field. But that's extra information that might or might not have answer future questions. Load is applied to the shaft and slows it down. The rotating magnetic field continues to spin at this same speed, and applies more electromagnetic induction on the shorting bars, increasing the strength of their magnetic field and thereby increasing for and torque on the shaft. However, there is no limit to how much load each motor can handle before it stalls or the winding overheat. And for that, you need to review your motor's data plate. So now I want to show you the graph of the torque. So here, the breakdown region, you can see the torque is going to normally, but motoring region, torque is going to the upside, and when generating region is going to downside. What I say. So now I will talk about the starting methods of 3-phase induction motor. An induction motor is similar to a polyphase transformer whose secondary is short-circuited. Thus, at normal supply voltage, like in transformers, the initial current taken by the primary is very large for a short while. Unlike in DC motors, large current at starting is due to the absence of back EMF. If an induction motor is directly switched on from the supply, it takes 5 to 7 times its full load currently, develops a torque which is only 1.5 to 2.5 times the full load torque. So this large starting current produces a large voltage drop in the line, which may affect the operation of other devices connected to the same line. Hence, it's not advisable to start induction motors of higher rating, generally above 25 kilowatt, directly from the main supply. When we talk about the various starting methods of induction motors, firstly we have 3-phase direct online starter. You can see that this model of the DOL starter, and we have the second one is starting of circular cage motors. In the circular cage motor startings, we have 3 starters. This one is the stator resistor starter. We can see the model of this. And second one is the auto transformer starter, and the model is you can see all of them is from there. It's working together. And the last one is star delta starter. You can see there and start from there. So now I want to talk about the speed control method. We have here pole changing methods as multiple stator windings, method of the consequent poles, pole amplitude modulation and stator voltage control, supply frequency control, rotor resistance control, and slip energy recovery. So, how can we reserve the direction of rotation? Also, when rotation connection, it's coming L1 to T1, L2 to T2, L3 to T3. But from here it's turning to right side. But when we change the connections with L2 to T3, L3 to T1, it starts to turning the another side. Just we should change the connections. That's it. So the power factor of induction motors varies with load, typical from around 0.85 or 0.98 full load to as low as about 0.2 at no load. At no load, an induction motor derives a large magnetic current and a small active complement to meet the no load losses. Therefore, the induction motor takes a high no load current lagging the applied voltage by a large angle. Hence, the power factor of an induction motor on no load is low. You can see the power factor graph here. The output to input ratio is called the efficiency. The rotor efficiency of the 3-phase induction motor is the ratio of rotor output per rotor input, which is equal to gross mechanical power developed rotor input, or PM over P2. Therefore, the phase induction motor efficiency is the ratio of the power developed at the shaft per the electrical input to the motor.